Hello everyone, welcome to another Chem Complete lecture. And in today's lecture, I want to tackle the subject of how to analyze GC printouts or gas chromatograph printouts. So in general chemistry and organic chemistry, it is a very common laboratory experiment to involve gas chromatographs in some way, where you basically either form a product, you do a distillation, or you're just trying to separate liquids, and then you analyze the results by using GC. So many students get confused as to how to interpret these graphs and how to work with them. So that's what we really want to take a look at here today. So you can see I have a general GC that I've created up here. So on the x-axis, you see the retention time in minutes, and it's ticked off at 1, 2, 3, so on and so forth as it goes down. So this is the number of minutes that a compound has spent since it's gone into the GC injector until it actually hits the detector. So to give you a little bit of background for GC, when you have a GC instrument, you're going to take your sample, it could be a gas or a liquid, up into a micro syringe, and then you bring that over and you inject it into the GC port. Now the GC port, or the injection site, is going to be heating at a very rapid pace, so it's going to have a high temperature. And the goal, once you inject that in there, is to get whatever is in the mixture to go into a gas phase. And once it is in a gas phase, it's going to continue to be pushed by what's called a carrier gas. That's usually just some sort of an inert gas like helium or nitrogen that carries the other gases through a very long internal column. So it's like a pipe that's twisted up for many feet inside of the gas chromatograph instrument. And when it finally gets to the end of that column and it's pushed onto the detector has a response, and that response is what triggers the formation of these peaks that you see in the readout. So the retention time is talking about the amount of time since the compound went into the gas phase after it was injected until it actually hits the detector and creates this signal. And then you can see on the y-axis is the detector response. So you can see the strength of the different responses. And it's also important when we start talking about this that we understand how retention time is going to relate back to each individual compound. So that's a general overview. Now the question becomes, if you have a printout like this and you know you have 3 different compounds, which compound is going to be which? So let's just use, for a generic example, X, Y, and Z. So you have 3 compounds in a solution, and they are labeled compound X, compound Y, and compound Z. And you need to figure out which one relates to which peak. So you do this by boiling point. Whichever one is going to have the lowest boiling point is going to be the one that would go into the gas phase first. So it's the easiest one to transition from a liquid to a gas. All right. Now, when you take a look at this, that means it should also have the shortest retention time. So the lowest boiling point is going to be associated with the lowest retention time. And then as you climb in retention time, you would expect the boiling point to increase. And that's how you can sort of mix and match your compounds to the individual peaks that appear on the gas chromatogram. So let's say, for instance, that X had a boiling point of 50 degrees Celsius, Y had a boiling point of 82 degrees Celsius, and Z had a boiling point of 37 degrees Celsius. So if we take a look at the 3 of these, the one that would have the lowest would be Z. So therefore, Z would be associated with this peak right here at approximately 3.1 minutes. And then the next one would be X, because it's 50 degrees Celsius. So X would be associated with the peak that's right around the 7-minute mark. And then finally, you would have 82, that's Y, and that would be this last one here that looks to be right around the 10-minute mark, maybe just shy of that. So it's pretty simple to match up your compounds and directly relate them to the peaks to identify which peak is talking about which compound. So then the next question that most professors want addressed is the percent composition. So when we talk about percent composition, you are dealing with the makeup of the mixture that you put into the GC. So in other words, if I take a sample of the mixture, what percentage of it is Z, how much of it is X, and how much of it is Y? And so that can be done by assessing the area that are underneath each one of these peaks related to the compounds. So when you get ready to do that, most of the GC printouts are going to have area associated with each of the retention time peaks. Now, those retention times are going to be what is used to identify the peaks, because the instrument, the GC, does not know that you're dealing with, let's say, ethanol or acetone or something of that nature. It just knows the retention time. So it's your job to match that retention time to the different boiling points, get the correct order, and then you can assess it. All right, so let's take a look here at how we would do this. All right, coming down here, if we take a look, we've got the area of retention for 3.1 minutes, the area of retention for 7.0 minutes, and the area of retention for 9.8 minutes. And they each have a value there. So you can see the one that has the most area underneath the peak is going to be the one at 3.1 minutes. And that has approximately 22,000 some, 375 there. All right. The area for 7 is going to be the least, and then the area for the peak at 9.8 minutes is going to be right in between that. So what do we do with this? You can see that what appeared right underneath here, I brought up the total area. Now sometimes this will be given to you in your actual printout, but sometimes you may have to calculate it yourself. And if you need to find the total area, it's very simple. All you have to do is sum up the area for every single peak of interest that you're going to analyze. So once you have this information, it really is pretty easy to find out the percent composition, because it's just going to be a ratio of the areas. So what we would do is we would say the area of peak, and I'm just going to use, again, a generic example, the area of peak X, right? And we're going to divide that by the total area. And then multiply by 100 because we want it as a percent. So using that formula, you should be able to find the area for each of these over the total area, and then that should give you the percent composition. So let's work on that together. All right, so for the retention peak at 3.1 minutes, we would need to take 22,375 and we divide that by 56,126. Multiply that by 100. And if you do that, you should end up with 39, and I'm going to take it out to 3 decimal places for significant figures, 866%. Now, based on this, you should be able to figure out the other two as you move along here. So let's keep going. You have 14,634 divided by 56,126 times 100. And that one is going to equal 26.073%. And then finally, for the last one, we have 19,117 divided by 56,126. You multiply this by 100, and you're going to end up with 34,061. Now, just to double check yourself, you should always add up all of the percentages, and they should come back out to 100, because the entire composition should be 100%. So there you go. You can look at the percent composition of each of the individual compounds that were in the mixture by utilizing this technique. All right. So anytime that you are asked about this in a lab, this is how you would go about showing the calculations for the percent composition that you obtained. And this information can also be useful in determining, let's say that we ran a reaction and there were 3 different products. We now know which one was the major product. It would be the one that was near 40%, the 39.866%. So what you could do then is say, okay, that peak is related to product whatever it might be, and you look at that product. And then you say, if this product was the major product, why would that be? And in your discussion section, you would want to discuss that the GC is confirming that it's the most prevalent product, and here are the reasons why you think that might be the case. So it might be sterics, it might be hyperconjugation and stability, so some sort of stable lower energy conformer. Okay, there's lots of different reasons that there might be. However, that's for you to decide. This can simply show you which one is going to be the most predominant product. So just briefly, if you found this helpful, you can always support me by going over to chemcomplete.com, and I have put together an entire guide on gas chromatography lab reports. So this will give a more detailed look than what we just went over in this individual video, and you will have everything to review over and over again in print. It gives plenty of examples, and it walks through anything that you would need to know. And as a bonus, this also comes with a full lab report. So I have a mock lab report that is based on GC analysis. So I wrote one on the dehydration of 2-butanol to create alkenes. This is a pretty common reaction that's requested in organic chemistry. Okay, so I've done everything, including giving an abstract, writing an introduction and background. You have your methods and materials, you have a results section, discussion section. So if this is something you are interested in, you can head on over to chemcomplete.com and pick it up for just a couple of dollars, and it will give you a fantastic template and walk you through how you would write a good lab report for gas chromatography labs. So other than that, thank you for learning with us. I hope everybody has a great rest of the day. Remember to like, comment, and subscribe. It always helps to support the channel, and I will see everybody next time. Thanks, guys.